He's having parking lot problems, so I guess we can just start, and any material he misses, you can just watch online.
Oh yeah, I forgot about that. That's an option now.
Yeah, so hi everybody, I'm Steve McMahon. I'm going to be presenting persistent data structures today. So the motivation is sort of mutable is bad. That's sort of obviously what we've been talking about for a long time. I have this really simple code where you have an array 5 and 10. You set y to x, and then is y a pointer to x? Is y a copy of x? And it's really difficult to know. So if I change y at the 0 index to 7, what is that going to do to x? That can be really difficult. And then the other problem is immutable is slow. So if we have, let's say this code over here, where we have a list, let's say, or a vector 5 and 10, and then we want to cons 8 onto that, or we want to append 8 in Haskell, we have to kind of potentially copy the entire array to add that element on. So in the real world, what does that mean? Well, a lot of times we'll have something like undo. How do you do undo? So if you don't have any state, it's really difficult. So you would have to have some sort of a transformation function to get back to where you were. So you have to know what doing something is and knowing what undoing it is. And that can be really difficult. So some of the examples that I run into a lot with JavaScript and programming on the front end is you send something out and it has no state. People start doing something, let's say they're entering a form, and if they refresh the page, how do they know where they are? They might have lost sort of all of the stuff that's in the form. So a lot of times what we'll do is we'll send snapshots back to the server, we'll cache it, and then when they refresh, we can send that back, or we'll cache it locally on their machine. But it's really difficult to get the exact state back from where they were. So if we're using persistent data structures and working immutably, we don't have to worry about that. We can have a snapshot all the time and sort of begin where that snapshot is. And because functions sort of behave the same way with the same input, we can guarantee that if we give them the same input that they had at that point, which I guess would have been the output from right before what they did, they can kind of pick up where they left off. So there have been a variety of persistent approaches. So the first one is copying data structures, which we already kind of talked about. The second is fat nodes, and third is tries. And I pronounce it tries just because it's confusing with trees, so you can pronounce it however you want. So the idea of fat nodes is, let's say we have an array, and we want to keep the history of everything that we're doing all the time. So let's say 0 has changed once, the index at 2 has changed twice, the index at 5 has changed, I guess, 4 times. So in this case, you need to keep every possible history. And that's not really a big deal, but let's say that I want to go deep into the past. Well, now we're really traversing a linked list, and that can be really slow. So keeping the history within each node isn't really a good way to go about keeping histories, because it can be really slow as you get further away from the past. So the other alternative is using tries, and tries essentially are like Huffman trees. And instead of using 1s and 0s, you're sort of using the actual values. So you'd be using like A and then R and then T or whatever to sort of traverse through and search for something. And what we're looking at here is, so we had XS. So let's say that that's maybe a list or something like that, and it's represented as a tree. And then we want to have YS, which is going to inherit some of the features of XS, but it has some new features. So in this case, it's going to inherit everything from XS, except we're inserting E. And so you can see we create these G prime and I want to say that's F prime, these sort of meta nodes where they're not actually storing any value. It's just sort of a way to indicate that something's different from the original structure. And so what's really nice about these is that they're extremely fast to search. So it's not quite as slow as the fat node situation. So in Clojure, they're using these types of persistent data structures constantly. So each one of these collections, sequence, lists, vectors, maps, they're all internally represented as trees. So this is sort of what the Clojure persistence model looks like. What you're looking at is sort of a modified version of the last of the tries that we were talking about before. So each of these is a hash, and then they take the 32 bits, they create 5 little sub hashes, and then they put either these leafs or these other nodes underneath. And so it makes it really quick to sort of find whatever leaf node you're looking for. It's a little bit faster. They're called hash array maps. And so it's just a little bit faster than sort of the naive approach of tries. And this is actually not Ritchie's idea or Closure's idea. This is something that he took from a paper from, I think, 2001. So what that sort of leads to is obviously all of the data structures in Clojure are persistent, but they actually created Datomic, which is a fully persistent database. So the way that that works is the same way that they create a new node each time new information is added, and while preserving all of the old information, they do the same thing with the database. So you're constantly creating new versions of the database that consist of almost entirely what you had previously in the database. So I'm not going to get too into the details specifically because I don't really know the details that well, but you have these different parts and they're all sort of, the fundamental idea is that they all serve the purpose that they're supposed to serve. So for example, the transactor is, so let me back up. The entire system is transactional. And so that's how they sort of keep the ACID transactions that you would typically have in a database. So they have this transactor, which is taking transactions. It's taking sort of changes in data or it's new versions and storing it to the database. But that transactor, and obviously it's making sure everything's atomic, but that transactor doesn't do anything for reads. So you could imagine it being sort of like a scribe who observes something and then he hands out the book. You don't need to go and talk to the scribe each time. He can just print out new books each time. And sort of you're just referencing the book, you're not referencing the scribe. And so this is sort of one of the main differences between traditional databases where the reading and writing is handled sort of, I guess, maybe by the scribe. And this type of model where you have someone who's sort of just writing and not reading. What that does is, you'll see here, he's updating the index. So that's sort of letting your query know how stale or fresh it is. And then the data over here, all the reads are sort of separate from writing. So it's sort of just letting you know whether it's fresh or not and sort of doing everything that it needs to do behind the scenes. So it's a really fast and really good model for databases. One of the main ideas for this to work, though, is that they're not talking specifically about place. So typically when we talk about memory models, we're talking about places. So we're saying, this is stored here, this is stored here, this is stored here. And it makes sense because for old data models, we didn't have a lot of memory, we didn't have a lot of disk space. But for, I guess in the last maybe 20 years or so, we've been getting increasingly more data storage. So what that means is that we don't really need to think about things as specific places anymore, but we can think about things as facts. And we can sort of talk about how a fact might be updated. So for example, if I lived at a location, I've always lived at that location. Or I should say, at one point in time, that fact was true. And so we're sort of divorcing the temporality from the actual fact of something happening. So if I said I lived at one address, and then I lived at another address, and I lived at another address, all of those are true, and really the only difference is the timing. And so if you can find a way to reference, okay, this is the current time is this address, you still have all of those other addresses. So if somebody's referring to where I lived in, I don't know, 1980s or something like that, I guess I wasn't alive in 1980s, but 1990s, it's sort of a very, sorry, it's sort of a very, I guess it's a very specific fact, but not a location. So I don't ever have to worry about updating those things. I can sort of just update what I'm looking at, I guess is a better way to describe that. So
you change now instead of changing the fact.
Yeah,
you just change
exactly
what now is.
Yeah, but the facts are always the facts because they never change. And so that's a very, I guess, intrinsic idea to not just Clojure, but to a lot of functional programming.
So is there any way that something can eventually become unreferenced and be
Yeah, so we have, like I invented any of this stuff.
Yeah,
so you have atoms and references. And so atoms and references are your way of sort of pointing at something.
Yeah.
So I can have a reference that says, this fact is, I guess, currently true. Is sort of maybe the way that you might think about it.
Mm-hmm.
And when that reference changes, that's fine. That has to happen atomically. That's sort of that monadic idea that I don't quite understand. But yeah, so the reference is changing sort of atomically, and then that's just pointing to a new fact. But those facts, those values, are always the same. They're always facts.
Okay.
So And it makes sense because for most data, it's not going to become untrue, like in life. It's just maybe not true this moment, or it's less true than something else. So it's sort of maybe more pointing to the truth right now, but it doesn't negate the fact that it might have been true at a certain time.
Sounds like these data structures are almost a philosophy.
Yeah.
Okay.
So yeah, I'd like to thank our sponsors, PHP. Just kidding. So do you guys have any questions? I know I kind of rushed through that, and it's sort of all really new material, but.
How do you keep one from clobbering over another if you have multiple people working on it? Is it like keeping the freshest stuff first?
Right. So that's why everything's happening atomically. So once you enter that atomic state, you're sort of guaranteeing that like you have the most, I guess, the most recent reference. But the underlying data is never changing. So nothing's ever getting clobbered. You might just not be looking at the most recent thing.
Yeah.
So so the idea is really just to keep you in the present rather than sort of worrying about whether the data is present.
Allowing the undo and yet allowing somebody to hit the freshest, which is the wrong one, before the undo happened.
Right.
So keeping an index of which one you're currently on could eventually pose the hardest threat if somebody did too many undos.
Well, isn't that what the transaction manager you were showing did?
Right. So the transaction manager is just managing when something's written.
Yeah.
It's managing that the database is updated properly.
But it doesn't necessarily say that the one that you're
right. It's another separate issue where you're referencing the most recent data, but it's not necessarily that the writing is forcing you. It's sort of asynchronously flagging and saying, hey, it's dirty now. So look forward. So yeah, I don't know. I think this is actually something that I really want to get into doing and actually using personally. So I've been programming in Clojure, but I haven't actually done anything with Datomic or even really with a lot of really complicated data structures. So this is actually something personally that I'm looking at to sort of experiencing firsthand. Because I think it's difficult to talk about these things and research them without actually getting your hands like dirty with it, So
can we try any of these out?
Yeah, like I said, I don't have any references or anything yet, but I think what I'm going to try to do is later on in the semester, I'm going to be doing functional JavaScript, I guess, in 2 or 3 weeks. So I'll do that one, and then once we're done with that, we'll kind of come back to actually a real example using sort of Datomic in walking through sort of how you might use it.
Well, I have an example in Haskell that has no slides, so
that'd be great. Yeah, that'd be great. We can switch off.
Okay. Oh darn, it's on my laptop. Hold on. No, I won't be able to show it because I won't be able to do it without moving the laptop.
You can screen share. Why don't you just screen share on that laptop?
Ah. Okay. Then in that case, this. Okay. Well, in that case, you might have to move around to see it, but I'll show it to you on my little screen here. Oh, I guess I can do both. Ah! Okay, now I'm catching on. Okay, here you go. So you're probably more.
I think I guess I was 2.
So you're probably more familiar with the imperative style. Let me show you what this might look like in Haskell. So, and not might, I actually have run this, and it works. So there are several parts here. This is a function the same as you might see in just about any other language. We call it an action in Haskell because it's wrapped up in a monad called IO. Okay? And even though it is an action, these can also take on functions or actions of their own. So in each line, this is an action that takes an action. And you'll be feeding in exactly what you want it to do for each particular line. Okay? And finally, we're going to get together with this ultra tiny main action and run all of them. Okay? So this is, and despite the fact that this contains monads and it includes what most people consider to be the scariest parts of Haskell, these are actually more familiar to most people than you might at first expect. Okay? So we can see we're going to get some arguments and then take a histogram and print it out. Okay? Now taking a histogram takes us up here. And it does most of what you would expect if you were working with Java, let's say. This is basically a hash map that we just created. But we call it, it has to be within I/O. And the reason for this is that it's mutable. So this is exactly what he says is evil. Well, you know, in a way, maybe it is, because it forces all of these to be actions. You can't use pure functions on these. And they also have to be serialized. So you can't run multiple at a time. Okay? Now, the point we get here, we made our hash map, and then for every line, we're going to run this block down here, which is a function that takes a line. Okay, and for these, we're going to break it apart, extract the text from each break, and then run a function on all of the words that we got from that particular line. Okay, and the words here, we're just counting. So we want to find out, the goal overall is to find out how many times every word occurred in the whole file. Okay? So you could imagine that actually lines are unnecessary here, that we don't have to know line by line. But the good point about lines is that they inherently restrict the amount of data that you're holding at one particular time. So if you read the whole file, that could be a problem. In this case, in order to test it, I run it on like a 5 GB file just to make sure. And that's one reason that doing these actions is actually a really great thing, because you get control over how much data you're handling at a time. Okay? So here, we simply get the current value of the hash, increment it, which is done on the right side of the $ here, and then we assign it back to the hash on the left side. Okay? So this is all actually rather pedestrian. This, for example, is for line and file. That's if you're used to Python, that's probably one of your greatest idioms. If you're used to Java, this probably has about 10 or 15 lines in its idiom. Okay. Now each line shows a higher order action, and the point being here that we can pass on what we're going to do with this particular line, and then we run a loop on all the lines in it. Now loops in Haskell are actually function recursion. And in order to use function recursion, you have to use the fixed point function. So this fixed point function will pass its block to the block. That's why I called it me, because this function between do and me is me. That way we can call ourselves and keep going in a loop as long as we need. Okay? Now this is the overall way to do it in an immutable fashion, and it's actually, without the comments, it's pretty comparable to every other language's way of doing it. Okay? Now you can see immutable histogram is totally different, and it's a totally different way of thinking about the problem. So here we only have one action. We still have to read the file, so we can't make this a pure function. But we can handle everything all at once without handling any chunks. So in this case, we are saying that we want to read all of the contents of a file, which it won't do now. It's lazy. And we want to split them into lines. Still won't do anything. In fact, it won't do anything until this last line. We will take the words in all of those lines, which will now give us a list of lists. Okay. We'll run a immutable hash against it and fold. So folding is really common in Haskell, and it's very important. We start out with an empty map, and then we are going to pass the map and the new word to this function between the parentheses, and this function will give us a new map. So we're going to end up going back and forth, giving the map to the next function in Word, to the next function in Word, to the next function in Word, over and over. Okay? Apparently it's complaining that I don't have much battery left. Anyway, for each of these now you're going to have a map, one for every line. That's why I end up naming them lines, hists, and lines, words, so that you can tell the hierarchy of their data structure. Okay? And then the result is simply a union with plus of all of the maps. And this is what's really neat about these immutable data structures is they give you a lot of syntactic sugar for those kinds of things. So if you want to say, I want to add together all of the values with the same keys between a whole list of maps, this is all you have to say, unions with plus. Okay? And now that is going to be the finished histogram, which I print out. So you can do all of this in like 8 lines. Thank you. So, does this bring up any questions? I figure it should bring up a few. It's a whole different mode of thinking between these two.
Yeah, can you run it?
Yeah, but I found out the second one is so ridiculously slow that I don't know that you want to wait for it to happen.
Right now it's something smaller?
Yeah, I cut it down to 100,000 lines. I think that shouldn't take too long. Yeah, actually I did it right here. Let me see if I can bring up the size of this a little bit. So, you like 9-point font, right? Wouldn't me to bring it down a little bit more? 15. Okay. Now I should be able to. Hello? I thought that's what I just did. Oh, there we go. Okay, so now you can see what I'm doing. I have a empty, yes, asserted, now it's empty terminal. And I can say here, compile the mutable histogram. The garbage in here is basically just telling the compiler that I wanted to include all of the packages that I installed already for this. Okay, so O2 is telling it to optimize to the best that it can. And now we can run histogram. Okay, and give it the tiny input. And it returns that whole long histogram, which is going to be kind of long to read, so I think I will redirect that to null. And time will tell us how long it takes. So in this case, 3.8 seconds to run the, on how many lines? Let's see, WC, I'm going to tell input tiny. On 100,000 lines, yeah. Okay, now in order to run this on an immutable histogram, it will take a little bit longer. But not hugely. Even though you're doing a whole lot of theoretical copies for your whole data structure, it only costs you about 2 seconds. So this is because underneath the data map is actually implemented like a Patricia trie, or trie, as you called it. Okay, I'll go with that. It's a trie. And as a result, every time it's updated, it only usually changes 3 or 4 nodes. There are actually even faster ways that you can use a hash array map tree, and it will be about twice that fast. So overall, you end up paying pretty close to nothing in order to get 8 lines instead of about 2 pages. So,
Sounds bad.
yeah, it really isn't too bad for the change in the length of code. But you also have to ask yourself, this is a totally different way of thinking about the problem. That you're saying that you're making changes to the whole thing. You're not doing one operation after another to a limited set. So maybe the analog to this is oftentimes if you're used to SQL, you're forced to act as though you're working on the same column of everything in the table. And here you're doing basically the same concept. All right, any questions?
Yeah, I'm completely new to functional programming.
Yeah.
Just curious what exactly is folding does.
Oh, okay. Probably it would do best to see an
Hold
example.
everybody up, I don't know. Yeah.
No, no, this is the end. So that's why we ask questions at the end.
Okay.
Okay, so the best way to think about this is probably from an example. So let's say we have the numbers 1, 2, 5. Okay? Okay, so that's pretty easy. Now, if I ask for it to fold using plus and starting with 0, everything from 1 to 5, this is what you'll get. Sum of all of them. Okay? Now, it probably also helps to think of it as this works for any data type. So you can also say this. I don't have it right in front of me, so I have to look over once in a while. Is an, probably want a space in here somewhere. Okay. And just to make the point that it can also work with these empty strings. Example. Okay, so you've got another one, but now for this plus isn't going to work and 0 doesn't make any sense. Okay, so instead we have to start with an empty string, which is a string's version of 0. Okay, plus still doesn't make any sense because that's not overloaded like it is in most languages. Instead it's actually concatenation, which is 2 pluses. And this is what you'll get. You simply start with nothing, and then you start merging them on using this particular function up until you get to the end. So it looks a whole lot like, basically the exact function that you're running here looks like this. This. It'd be nice if it was basically exactly the same. Plus is. Okay, now we're going to end there. And remember that we're running the function again. And on the left will be whatever comes out of that concatenation. And on the right will be the new item. And this just keeps going and going. Okay. And I actually forgot one piece. So you see that when we started, we had an empty string. And that's what's going on here. So the first one, it gives us the empty string. Okay? Now, there is another curious bit. If you watch really closely, you'll see that I actually use fold-L without a single quote. Okay? Now, the difference here between these is that fold-L with a single quote forces strict evaluation, meaning that the moment that it is required to come up with the result of fold-L, it won't simply execute one item and pin all the rest of them. Instead, it's going to execute the whole fold-L result and then give it to you. And it's going to append them together instantly. Because if you don't do this, it's very common that you'll come up with thunks, they call them, which are unevaluated expressions that are waiting to be evaluated and often keep things from being garbage collected. So most of the time,
it's lazy, because it's been lazy for you.
Exactly, it's lazy, and it can't guarantee that you're not eventually going to use that expression. So it can't delete it, and it's still trying not to compute it. But it turns out it's actually kind of useful on occasion, and this is one of those places that it's immensely useful. You can see that in immutable histogram here, I read the whole file, and this is a list of, this is just the whole string, which is a list of characters, right? But it doesn't evaluate it. Therefore, it doesn't take up all of memory. Okay? Yeah. And you can see how fold-L is one of those neat things that only makes any sense with an immutable data structure. You can add this stuff together and keep adding it all on, but it's not really the same as a loop.
So let me understand it better. So strict evaluation, you said it's not going to, or you said it's not actually going to compute until it does all of the folds?
Yeah, so basically with this, the strict and lazy evaluation give the option simply to short circuit the requirements. So like you're basically saying that this function, in order to complete its result, is data dependent on a couple of inputs, right? So by using seek, you're saying you're making a transitive dependency. You're saying that this depends on what that function depends on. So you're forcing that function to be evaluated too. It's called SEQ for sequence. Okay? Now, using that neat little function, you can chain it together, and that's what fold-L prime does. It requires the sub-expression to be evaluated as well. Just look at this. So you can see if I'm asking for this, it will give me plus plus and. But then this is going to be a thunk. So it's not going to figure that out. And it won't be until I require it that it's going to figure out this thunk, and then it's going to figure out this thunk, and then the next thunk, and eventually it's going to run out of memory. Okay? Now, instead, when we use fold L prime, it simply says the moment that you get this outer thunk, it will require this one to be completed first. That's the sequence.
Yes.
Yeah, and so it's going to go from the inside out rather than the outside in. All right?
Makes sense to me.
So who wants to try it? Can you read in lines? Show me the first 10 lines or something from a text file?
I don't have anything installed.
Well, does somebody have Haskell installed? It's not too hard to install. In fact, I have it here. You can show everybody.
Yay!
Yay.
I'd put you on the spot just a little bit.
It does, but that's the fun of it. I mean, you're on the spot in front of, what, 5 people?
You said, what do you want to do?
I'm going to take a file and read the first couple of lines from it.
Just first couple of minutes.
Yeah. Do you know how you might try to do that? I can type it if that makes you feel better.
Let me see your code again in full, just to try to figure out
Okay.
how you actually.
So take a look at it here. One building block that you're missing for that might help you is to say, take 5, say, from this infinite list that goes from 1. Okay, let's not make it infinite. Let's just make it huge. Okay? It will give us the first 5. Okay. And it doesn't evaluate the rest. All right? So that should be the building block you really need for this.
Yes.
Yeah. Hold on. I'm going to raise the price a little. You get a cookie if you complete it. Okay?
I can eat cookies, but I can try.
Okay.
I'm still trying to figure out how you, let's see,
What are you looking to do?
just
I want to read a file
print
and
first.
print out the first couple
In
of
the
lines.
terminal?
Yeah, in the terminal.
You already
Oh, in the
have
terminal,
everything
okay.
imported. You already have everything
Yeah, you have to
imported,
check
right?
that the right thing is important. If you look at the top, it will tell you where these came from. Well, I mean, I can tell you, but you might as well just go ahead and find out.
Yeah. So I have to get the system environment in, right? Or not
no,
really, because
you
it's
don't
already
actually-
in the shell,
Well,
in the
look,
terminal.
What's in the terminal so far? What we're asking is how much setup do we need to do this right now?
Right.
you don't have to get ours because you already know the file name.
Okay, so
Okay, and if you look up near the top, there's data text lazy IO. Okay,
Mhm.
and that will allow you to use h get contents.
can I be lazy and say just import data text lazy?
No, you can't because
can't?
you
You have
won't
to
get
call-
the stuff inside it transitively. You only get
Okay.
the outermost.
Oh, okay, I see.
You see, this whole theory goes
Haskell's as lazy as physically
as
possible.
lazy as it can be.
And then it overwrites itself.
Yeah.
So I guess first we need the IO,
Yeah.
right, and text.
Walk through it.
Okay.
No,
Let's yeah. You see, you need hget contents in order to get the whole content of the file. That will probably
And how do you know
use
which one of the packages it's? Oh, H, right? Wait a minute.
No, it imports everything from it. So you wouldn't know. You just
Okay.
have to ask.
Yeah, all right, I see. So
Yeah.
the get content's coming from the data text lazy IO.
Yes.
So I guess I have to import that. Right?
Yeah. There you go. Okay. Now you have to figure out what type handle is. The handle actually comes from with file. And this is going to be kind of a pain to try to open the file.
That's what I'm saying. I don't know that the terminal's gonna work so well for that one.
Okay.
Yeah, ick.
Then just edit the original file. Work on it.
Okay.
Yeah,
Yes.
I think that.
Do that. That'll
Do you have a
save
copy saved so I don't have to?
Yes, it's in Git.
All right.
Git, the ultimate immutable data.
I cannot edit it. I have to go here. Wait a minute. I'm confused.
Uh-oh.
There you go.
There you go.
Oh,
Sorry.
that top corner thing.
It's on the screen to the left. What you're seeing
To the
there
left?
is actually a picture.
Okay, there we go. I had to move the cursor to the right. So the only thing you want to do is print.
Yeah, print out the first couple of lines.
Wait a minute. Okay, sorry.
I don't think that'll cut it. Okay.
No.
Now, you can see the print is an action. So it needs to go in one of the do blocks, which I would say put it right here where your print already is. Okay?
You put a dot in the T lines,
You do?
on let
Oh.
content line.
Oh.
When ease.
Nope. There you go.
Okay, and since these are lazy, even though they're defined, you don't have to get rid of them because they won't be evaluated unless you actually use them.
Column, right. So I just modify this print essentially.
So what do you think will get you the lines that you need here?
I want the content of the file itself, but not the histograms, right?
No, just the file.
The files.
Mhm.
So I have to get, I guess, take 5 from the content.
That'll give you the first 5 letters.
5 letters.
Instead.
Okay, content lines, right?
There you go.
All right. So can I just say take 5 like that?
Yeah. And then
Okay.
content line.
There it is.
And see what happens with that?
Yes.
If you go down here, you can use Control D to end the terminal. If you go up a couple, which one is the immutable? Yeah,
Right, that's the one.
compile.
Right.
Okay. That didn't run it, that just compiled.
Yeah.
So if you go up again, you'll be able to find where you ran it. That one.
But not
that
time anymore, right?
Yeah, you don't have to know time, and you also don't want to redirect the output to null.
To null,
You'll be
right.
able to tell.
If it worked or not.
There you go. That's your first few lines.
Cool.
And your first few lines of Haskell.
Yes, that's right.
Okay.
So it automatically actually puts them into an array of, because that's what that, or not array, but I guess it's a map.
It's a linked list.
Linked
actually.
list.
I think you earned your cookie.
All right, thanks.
Definitely earned this book.
All right.
Cool. Thanks, guys.
I'm sure you'll stop, right?
Really, I gotta start somewhere.
Mhm.
Wait below him.
Now, if you look at this, you'll see that was pretty easy to do. But if you look back at mutable histogram, you'll see it's going to be kind of a pain to be able to do that kind of thing. Because you'll have to muck with each line to handle line numbers, probably adding in some counter. Okay. And then you'll have to figure out how you're going to pass in how many lines you want. Maybe you'll just write it in as a hard code. And then what does this mean for line proc now? Does line proc just do prints? I mean, it could. Okay. So you probably could edit that. But it would take more than 1 or 2 lines to get it to do it. But now that you use the immutable over here, it only takes, did it take you a line? No, you just changed out a
Just
line.
change one line, right?
Yeah.
Just curious, since you have a fold-out prime, does that mean it's gonna actually do the whole file? Or, but I ran pretty fast, so I guess it did only first, whatever the.
No. Remember, it's just changing the transitive dependencies. It doesn't force the whole thing to be run immediately.
I see.
So with fold-out prime, if you called on count line, suddenly you would need it.
Oh, I see.
But in this case, you never called count out in line, so fold-out prime was never called, and so nothing happened.
So it only essentially ran 5 times whenever I say take 5 from content points, right?
Yeah. And this can become kind of pathological if you're dealing with really small quantities of text, like 1 line. So underneath it all, the compiler actually replaces it so that it's handling blocks of disk block size. So it tends to be about 4,096 characters. Okay. So that sounds pretty cool. Anybody else want to try this challenge? Do you think you can do anything else with it?
What else?
What else is there? Can you tell me the maps for only the first 5 lines?
Lines or words?
The first 5 lines. What are the counts in all the first 5 lines? It might help to undo his change so you can see this is what you would deal with. Right here.
Well, to the
What do I change?
finished his, we've now become, we need lines, right? We become line hists. And you need 5 of them, right?
You can type. You're allowed to type. And you know what? We even have another cookie.
I've had plenty of cookies.
Oh, okay.
Way too many of those plenty of cookies. You're gonna want to a list or do you want the print take 5? Oh my God, who can see this angle? Why could somebody do such a thing?
Wait. So just think for a second what the output is going to be. It's one map, okay? And that map represents the counts from the first 5 lines.
All
Okay?
the line words.
There are actually a bunch of different ways you can implement this.
Okay.
And all of them look pretty much the same. They're going to involve take 5, and then you decide what goes in after take 5.
I would think it would just be line hists.
Okay.
Am I
Show me where to
wrong?
put that. Yeah, that's one of the solutions. If you can find, nope, it doesn't go there.
Okay.
Wouldn't work there. Yeah, in finished hist, for example, it already computed all of the line hists, so it'd have to be before that spot.
It's in the line hists, and you're making a map of it.
Okay, then you want to split. Am I being too vague here?
Way. For
Right.
me, you are.
Okay, well then I'll say
Come on, come back to
Is
me.
it in
I
here?
know, like
Line
3
hist?
lines of Haskell.
Yeah. Well, you're gonna get your 4th. Okay, so you've got line hists, and this is going to be one of those lazy lists, and you can stop it at 5 here, or with lines words over here. This is another list of lines. You can stop it at the 5th of that one. It's also going to be in content lines. You can stop it at the 5th of that.
Good gracious.
So whichever place you like it.
Why can't you call it at the end? I know it's going to be elevated for all of them, but can you still call it at the end?
No, actually it won't work, because by the time you get to finished hist, if you evaluate finished hist, that's going to run unions with on everything in lines hists.
Does it modify line hists?
No, it doesn't modify lines hist, but if you put it after this point, you would be printing out all the garbage from the big map, and then another group from the little map.
I don't know, but I mean, like, you said that it cannot go there. What did you mean then? Like, if instead of finish hists, I want to print to list the line hists, why can't we do that?
Hold on. Yeah, lines hist, you can print that. That's fine.
You
It will
can.
show you one map for every line. That's what the lines hist contains. Okay, but this of course won't work on that because it's not a map. It's actually lists. Okay, so if you wanted to show one hist for every map, one hist for every line, then you can do
Did
that.
you just do take 5
Take
of
5,
line hists? That's what I was gonna
No,
do.
take 5 of, something
Line
like that.
hists.
Yeah, that's what will happen. You will get 1 for each line.
Mhm.
If you want to do that, print that out. The fun of it, is the fact that you can try it.
Yeah.
So,
You're setting me up for failure, I can tell already.
does it mean that by this point, all the line hists are actually evaluated, right? So if all you were interested in line hists, you're probably better off doing it a little bit higher, so you don't have to compute the rest of the stuff, or?
If you evaluate finished hist, then yes, they will all be done. But she didn't evaluate finished hist, so they're not all used.
Oh, okay, I see.
She only did the first 5, so you're going to get 5 histograms. And that's all that will be evaluated. The 6th and on won't be.
But line hist is already used in the union with, right? Does that mean
It
that line
is, but this is only defined. You just defined the function for it. This is a function that takes no arguments. It's always the one above it. It's not assignment.
That's the break away from the assignment.
Yeah, I know, it's hard, isn't it?
It really is.
Yeah, and then what is assignment doesn't look like assignment. Up there as the left pointing arrow is assignment. But even then, the secret is that it's really syntactic sugar for another function. So things just get crazier after that. Okay, now you can try this and see what happens, but you have to save it first. Now, down here, recompile, rerun. Hey, look, no syntax errors. That's a good one.
That's really good for me, huh?
Okay, there you go. Now, what you'll see is you got a list. This is the outermost left square bracket. And then a map, a histogram, is represented as from list and then a list. So these are key value pairs. Okay? Now, this is the one, this is the map all the way up to here for subdichotomous 1. You can see everything between these is the histogram for the first line.
Mm-hmm.
And then there's the second one, third, you get the idea.
Yep.
Yep. So you've got 5 histograms.
Mm-hmm.
Cool.
What kind of lines do you have there?
Oh, I actually generated as randomly selected words from the dictionary.
Okay, I'm like, wait a minute.
Some interesting data there.
You know.
Well, I always use subdichotomous twice a day. Okay. Now I can see I was very vague because this was not at all what I was thinking. But it's one correct
But that's
answer.
what you said.
But you want the histogram all 5 lines.
Yes. So how would you do that? It's the same thing moved over a little.
We'd want to do it up here.
One of those. It's either in the lines hists or finished hists line, whichever one you prefer.
Well, it's here. You could just take 5 here, right?
Bingo. But wait. You realize this has to now be in parentheses because you wanted to evaluate before you give it to unions with.
Is it implied or is it not implied?
No, it'll be passed as a function.
Oh.
So take 5 would have applied to union with somehow?
No, what would happen here is you would
be evaluated when it needs to be evaluated, wouldn't it?
It would be, but it would be a function without any arguments. So instead, you would have unions with would be passed one function, another function, an integer, and a list of histograms.
Oh, right. Good call.
So instead, you have to stop it.
Because it's the spaces that count.
Yeah, the spaces are like commas in every other language.
Yeah.
Okay. So now you got that. Save it and try it. The thing is, it's not going to look a whole lot different because there's no second subdichotomous. And look, still no syntax errors. And people are so afraid that they won't get it to work. Okay, yep, see, not 2 of anything. Subocularly, Londonesian.
Yeah, well, you pick some odd text there.
Hastatolanceolate? I'm not even sure what that
These
is.
are not really real words. Gives you
Okay. So now do you feel that you understand this pretty well?
To an extent, yeah, I guess.
Okay.
I guess I can start thinking through this and kind of understanding how evals work, I guess, and lazy parts.
Okay.
You want to take a look at this real quick?
Okay. What do we look at?
It's been since November, and I don't remember. How do I get that going? Let's see.
Oh, environment is spelled with a capital E.
There you go.
Oh, you get completion for that? That's
Yeah, sounds
nice.
like it.
You don't have to remember it all.
Yeah.
No. Okay.
It's the little
So
things in life.
then I don't need to actually install those, right? They're just
No, system environment is included,
okay.
but data text is not.
So I'd have to do
String instead.
Okay. So if I wanted to include this, it's just I would just install it through Cabal, right?
Yes.
In that project directory.
You install text. Do you have anything? No,
let's
it's
go
just
up.
text.
Here you
So
go.
is it Cabal install data or Cabal install text?
Cabal installed text. Sadly, there was no really convention over what you're supposed to name the packages. So they might have
So
names that
it's
have
random.
nothing to do with what they were imported as.
But that does give you the data.text, right?
It does. Yes.
Okay. It's crazy.
And including all the stuff under it. But that's also not guaranteed. You can
Good.
name yours data text lazy, someone else names theirs data text, and then it would look as though yours was a sub-part of their project, but it's not. It's just whatever you decide it to be.
So Cabal is like a package manager?
Yeah. It's like NPM, whatever.
Or how many are there now? There's like pip
Many.
for Java. No, pip for Python.
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 Yeah.
Okay, and then Gem? Or is it bundler?
Gem is Ruby. But bundler is another one I think for Ruby. I think
Okay.
too.
Easy install. Wasn't that another
That's
one?
Python.
Yeah, and then distribute and setup tools
Mm-hmm.
for
Python.
And then,
Half of which are now.
yeah, dead. Then wait, Maven and Gradle?
Yes.
Well, those are more like, I guess those are, yeah.
Maven is for Java.
Those are almost like task runners though, more than.
No, they actually import
Yeah.
jars. Like you just put the dependencies and then maybe like please test.
Yeah, that's how I do it. Like, that's how I do it.
How do you install them though? Do you install them?
I guess it's.
Oh, okay.
What is it? Is it
MDN? I don't know.
Well, I know it's MDN command, but I install it, which I guess compile it.
Yeah.
I don't remember how I installed it.
I don't remember either.
Yeah.
When I
saw-
installed the clips, I had it, and I didn't care.
Yeah, I saw a tweet. Yeah,
Where
I have to read it.
Where is it?
I have to read the tweet that I found a little while ago.
So is the in parentheses at the top, that's sort of different from what we've done, is that sort of,
Oh, wait. There are a couple of different ones. Like the one with Prelude or the one with System.io?
I did those too.
yeah, so I'm not doing anything with Prelude, I was just looking at like, for example, data list fold L.
What I'm saying is, I don't want anything in data list except the function fold_l prime.
You're saying specifically just this one?
Yes. Well, that keeps you from polluting your namespace.
So if I did
Sometimes,
something like data list as something, that would still be fine. So I can still do it as data list fold L as DL or something.
yeah, but then, well, no, you can't do it with one function. You'd have to do it with a whole
Package.
package. Yeah.
Oh, really? So I couldn't
Yeah, you can't just rename one. Not as far as I know.
really. Is there any way to maybe do data list as DL and then do the fold L, or you can't do that either?
Yeah, you can. You can just set fold_l prime in your default namespace here equals dl.fold_l prime, and then that'll be a synonym. In fact, I'm pretty sure the compiler will even completely erase any overhead that might have.
So how would we write that up
Oh, simple.
as well?
Import qualified data.list
Okay.
as DL.
Qualified.
No, wait, data.list.
So qualified, you just basically saying you rename it as particular values.
The qualified and the as are just, they go in the same rule in the syntax.
Now, data.list,
A capital letter. You have to pick capital letters.
yeah. But-
Whatever you want to name it. It doesn't matter. We're not even going to use it outside of the line right after it. Anyway, it has to be capital.
That's only one letter.
No, it can be however many, and it has to start with a capital letter. After that, it can be lowercase, but in practice, people just pick one or two letters. Okay, that seems fine. Now, in the line below it, you can define fold_l equals dlf.fold_l prime.
But so now you still have the polluted namespace though, right?
Yeah.
But
But you didn't pull in everything in DLF. You only pulled in one function.
Because you're importing qualified first.
The qualified does not import.
It imports, yeah, but it only puts it under a namespace. That's the only difference. Like, it really looks really ugly if you don't do that, because eventually things become really crazy, especially like insert, say, in map. And now maybe you want to map in a set and a list, and these all have insert. It will become really confusing really fast, what you're actually doing. Type errors galore. I mean, I've done that a couple of times. Like, at some point, you just want to throw the laptop. Yes, why doesn't it work? Okay.
Will the compiler actually complain about the clashes in namespace?
Yeah, it will.
Oh, it will. Okay, so it's
Not-
not like it's completely it's like
Not until you use it.
randomly one.
No, it's not until you use it. So it's like you could have multiple insert widths, but it's only on this line where you use it that suddenly the compiler isn't sure which one you want, then it will complain. Yeah. But it's not one of those phases of the moon, so you'll never get it compiled without it.
I see. So the prime thing actually works on any
No,
function where you-
it doesn't. There are just a couple functions that are named that way.
Oh, I see. Because I see insert with is prime.
Yeah, it is. And that's a real convention though. Like, I don't know, maybe 2% of the functions in Haskell have variants like that. And usually they're ultra simple, tiny variants based on the original one. So it ends up being just like, take the first item and then seek and then the second item or something like that. Okay. Now, one thing that I had expected you would have some confusion about is with path, read write mode, handle, do. Does this make sense to anybody? No. Total gibberish.
Get the file in the path,
Mhm.
read and write it.
I think our native Python programmer probably
Hmm?
is as ahead of the rest of us. So the situation being that in Python you have with a specific file, you
Yeah.
can say with open file.
Yeah.
And then followed by an indented block, and it has the same meaning as this.
Mm-hmm.
Okay, but in this case, what we're saying is this is a exception catching block.
Yeah.
Okay. Yeah. So if anything goes wrong in your function here in do, then in the stack will move back up to with file, and with file will catch the exception, and then close your file, rather than leaving it open. That makes sense? It's just a try catch in most languages.
And with file is the function that's gonna catch.
Mhm.
And you
With
have to
file-
further down.
Yeah, with file runs your function, and if it comes back up with an exception, it will catch it and close the file. It's really a tiny function.
And
But it's
read
a
write
nice
mode is, what is it, opening the particular path?
Yeah,
Mhm.
that's just actually in Haskell you get pretty interesting sum types. You probably haven't heard of them. They don't exist in most languages. And let me show you what it looks like, even though it'll be kind of tough to give a working example until at least next week, which is what I'm planning on doing. But you can say in Haskell, I have a specific data type, and I'm going to call it a tree. This is one of the really common ones.
You can actually see it on that screen.
Oh, yeah, I do. Tiny, but it's there. Okay, so I have a tree, and I am going to define this as either an inner node that contains trees, or it can be a leaf, and it will contain text. And that's it. That's all there is.
Okay, fine. You lost me.
Okay, so the concept here, it's a sum type. So this is one of those situations where we're no longer saying that this is the properties of tree will have either all the properties of inner node trees, or it will have all of the properties of leaf text. Now you're probably used to subclasses and such in most languages, especially object-oriented languages, where you can say and. So if you inherit from two classes, you will have the properties of all of both of those classes. Okay? Now in a functional language, you're also given the ability to choose or. So it will either be an inner node with all of its properties, or it will be a leaf with all of its properties. And you can attach whatever you want to it. Read-write mode is one of these. And you don't have to attach anything to it. So if you decide that you want empty trees to look different from inner nodes, you can say one of the options is nothing. Nothing is actually taken. So it would be confusing to call it nothing. Maybe you would want to call it empty or something like that. Okay?
And what is the syntax again here, where you say internode and trees? What are you saying exactly?
Okay, so I'm saying that an inner node is it's created by its constructor. This is inner node here is actually called a constructor. And if I say inner node, then that will be a new function. And I will have to pass it something that matches its type. In this case, it would have to be trees. So one of the correct answers for inner node here would be another inner node. Okay, but then this brings up the question what I'm going to do next. Okay, I don't need the left square bracket. Okay, and eventually I could get to the point where I say I want a leaf, and that one will be zilch, something like that. I don't know.
Hey, Zilch.
Yeah.
That's pretty
Okay. Okay, so that's what it contains. And since this is a list, it can contain something else. And we will say it has, what, a leaf? Okay, and next it will have an empty. No, and maybe we'll have another leaf.
Trying to figure out what's the scope of that or. Is it applying to everything after internode, or is it trying to?
No, it applies, it's the least binding. So there are three regions here: internode, leaf next, leaf text, and empty.
Mhm.
So leaf has nothing to do with internode. There's no overlap here. And the empty has nothing to do with either of them. And all three of them qualify as a tree, kind of like an interface.
So it's not green.
Now, what really makes this amazing is when you combine it with case expressions. Now, we're just throwing out syntax here. Like, this is not a function, so that's one reason why my editor is having a fit. I mean, it expects me to indent something here in a function. Okay, but the general concept is, like in a script, you would say something that says, hold on, case, and then I'm going to say cos.
There you go.
I'm going to define this so that you can get the idea of it. Okay, so now we can choose with A what we're going to do. One of them will be an inner node. Actually, leaves would be confusing. Let's call it child. Okay, and this is going to be one of those options. This is another function. Okay, then we're going to go from there. You get another one for leaf. Or you're going to be able to run some other function here. And it'll be just like, you could do a do or something else, you know, whatever it is, expression makes you happy. Okay, this is incomplete at the moment. If we received an empty, then we would get an exception because this is an incomplete, a partial function. Okay, now if we go in and we put in another thing for empty, maybe we will have, no, we'll call it empty string, you know, something like that. And now we all have, now the whole thing is covered and we'll always have some expression, as long as we fill in the stuff right onto arrows. Okay? That's it? Okay, see you. So now we have some types and a convenient way to handle them. And these sometimes can all hold stuff. Like, you might be used to the concept of an enum being kind of like these, but an enum doesn't have any arguments associated with it. And these can have 0 or more arguments. And they can even be of their same type.
Giving you a lot of options.
Yeah. And mostly it makes really pretty trees.
I'm just curious, should you actually say internet tree in the data line? Or
No.
trees?
Oh, haha, yes, you're right.
And that's what was getting me confused.
There.
Wait a minute.
You're
So
right.
it's recursively. Okay, got it.
Yes. English kills again. Okay.
I thought maybe some Haskell trick, you know.
No, but a lot of
add
times,
an S at the end of your class or whatever, you know, to get magic powers or something.
yeah. Well, if you've ever seen, sometimes Ruby can be like that.
Mm.
It can even be, you know, frightening how much is automatically done for you.
Mm.
You're not sure if it was actually what you intended or not. But like one of them, for Ruby, one of them is this pluralization that happens automatically. But then with Java, if you type in, for example, array or arrays, those are two different things, and lists are different things. And in Scala, what's even worse is that some of the objects go by the same name as their instances. So you can call exactly the same thing, and depending on which method you call, it will either be of the object or of the class.
Scare yourself.
Anyway, that's the general idea. I'm actually not totally sure that I got the syntax with case right, because I haven't used that but a couple of times. But you get the idea. The concept here is called pattern matching, and you can choose what you're going to do in each particular case. Okay? So, one thing I didn't go over yet, that's really cool about Haskell is it's really extensible, and one of the things that it's extended here is overloaded strings. So like, you can decide as an isString class, you can say that your particular class or your object can be instantiated as a string. So if you pass a string, it will also be called, it will be considered your type. Okay, so text is one of these. That you pass a string and it's considered to be text. And it sounds like, well, duh, they're synonyms. You know, it should be text. But underneath, the difference is that a string is a linked list of characters, but a text is an array of characters. So it has way lower overhead to use a text, but it's really inefficient to edit it because you have to copy the whole array.
It's good for reading, not so good for writing.
Yeah. But you do mostly transformations on these things anyway, so you're making a copy, and you might as well just do the copy and the modification at the same time.
As long as you have plenty of RAM and ROM, you're fine.
Okay, yeah. All right.
When you get limited, that you really start to care.
Anything else?
I'm just curious, the overhead of actually doing it through immutable, is it basically linearly scales with the amount of data you have to process?
It's all over the map. I mean, it can be everything from, linearly to logarithmic to n squared or more. You know, you have to think about the individual situations.
I see.
But in the case of that map I was showing you, even though in theory it should be logarithmic, or logarithmically worse, in practice the base of the logarithm is large enough that it doesn't really matter. It's like to the 16th. I mean, so base 16 of your particular size might only be 3 or 4, and times a rather small constant, it's not going to be very much.
Asymptotes pretty quickly, right?
Yeah. But basically, like for this, it costs you about twice as much. But it's just because it's mostly the constant factor rather than the logarithm that's changing anything.
Yeah, just wondering if that's the case, like, if it's linearly, then maybe that's quite a bit of an overhead. But if it's logarithmic, then I can deal with that.
Yeah, well, I mean, it tends to be like you can't guarantee a whole lot, but most of the time it's just linear. It can be logarithmic, but most of the time it's linear. Okay. All right.
And memory footprint, how would those be different between the mutable and immutable?
The same mostly. So if you just have to keep an eye on where you're being strict or not. If you're accidentally generating huge thumps, which can happen, then it will be terrible. But if you have if you are evaluating your thumps, reasonably in some reasonable deadline, then you're fine. It'll mostly be the same.
So good batch management is your
something like that.
best analysis.
Probably, I would be defensive about it. If you're going to deal with really large files, then probably you would want to take the imperative approach. At least with whatever the first thing that touches the file is. So maybe from the rest of that, you could have pure functions that handle 5,000 lines at a time. But I would probably cut it so that you have chunks or something like that. That way you don't end up with sudden unexpected chunks.
Interesting.
All right. Well, I'm sorry, I kind of took over your closure lecture.
Oh, it's great. I didn't have a lot today, so it's not a big deal.
Okay. Well, there we go. And I guess I'll be able to find this online in case you were interested.
So you said it's on GitHub?
These, actually, I need to make another pull request to Sterling's repository. But I have it on a fork.
Okay. I don't know who runs this. I guess who runs that sister. I don't know.
Sterling? Yeah.
Sterling, yeah.
He's the guy that just left.
Oh, okay.
Huh? All
So
right.
he's actually managing the GitHub for this.
Mhm.
Okay.
There you go.
Nice.
Now I think at this point we're probably done.